About 50 years ago, armed with the very latest deep space measuring tools, astrophysicist Vera Rubin went about an ambitious task to clear up some uncertainty about the rotation of spiral galaxies in the universe. But her data, Vera noticed, wasn't clearing things up. The Andromeda Galaxy was telling her that it didn't need to obey basic laws of motion. Vera looked at another galaxy and saw the same defiance, and another, 60 in all. Every galaxy she measured told her there was something wrong with the basic mechanics of the universe. For a lone astrophysicist, having to explain this was a terrifying thought. What Vera had discovered, though, was what some scientists now theorize to be dark matter. Her observations implied that there was an invisible form of matter that fills all of space, something no one has seen or produced direct evidence of, yet it is believed to make up most of the matter in the universe. What did Vera observe? Only that 400 years of observation was wrong, that what astronomer Johannes Kepler first observed as a delicate balance at work in the solar system was completely out of whack for galaxies everywhere in the universe. Lovely. Kepler tells us that the sun's gravity pulls things in that move past it. Move too slowly, the sun swallows them up. Too fast, and the sun's gravity can't hold on. When the motion of the planet and the gravity of the sun are balanced, then a stable orbit becomes the planet's pathway around the sun. But when things are spinning, there's a different calculation we can make about the relationship between two objects. Spin a heavy object around, the faster you spin it, the heavier it seems. Spin it fast enough and the object pulls so hard its force overwhelms us. We lose control and it flies away. And it is in this way that Vera's galaxies behaved strangely. The stars on the outside were spinning so quickly that based on the observable mass, there's no way by the laws of physics they could be kept from spinning off like that ball, or tear apart the galaxies altogether. It could very well be that our understanding of the basic mechanics of the universe need to be revised. But Vera realized there was another possibility to consider. If there was more mass than she could account for, a lot more, for holding everything together, the stars in the outer arms of her galaxies could move that quickly and yet stay intact. She looked for the missing mass. She could not find it. Great. Something that acts on all the observable matter in the universe, but we can't find it. Was it findable? Or was this something exotic that threatened to explode all of physics? The hunt was on. In the 50 years since Vera's discovery, scientists have puzzled over possible theories of dark matter. The most likely contender is that it is made of a fundamental particle, just like regular matter. If so, how will we find it? What if we don't? Or what if it's not a particle at all? Will scientists have to rethink some of the most basic laws of physics?
Good evening. It's great to have you here. What a great crowd. What a lovely day. How many of you were at the Oliver Sacks celebration last night? Yeah, isn't that something? The humanity and warmth of science and just the sort of universality of what Oliver Sacks did with his curiosity and his sense of human-to-human contact. Today we're going to talk about dark energy, right? Oh my God. Talk about chill fest. There's a point at the World Science Festival where I always feel, I don't know if you have this feeling, that you start to feel like, wow, this is amazing stuff, this is brilliant, this is fantastic. And then you start to feel, maybe I'm getting my chain yanked here. Did you listen to that video?
It makes up most of the universe. We can't find it. It doesn't act on anything. We'll just call it dark matter and leave it at that.
That's really helpful. For heaven's sakes. I mean, so scientists come to you with like, the universe's calculations are completely wrong. There's there's a major discrepancy. We're going to call it dark matter. We can't see it, but it's there, and that's what we're going to work with. How many of you out there, when you were little, had a secret friend? Yeah. Yeah.
That's right here. He's with me all the time. You can't see him, but he's my secret friend.
Is dark energy the physicist's secret friend? Board, can you bring the stage light down? Give me a total black here. Can we? I mean, I want to see some dark matter. Just light Q, dark matter. Let's just go with it. Go with it. Go with it. I know it's not in the script. Yeah, there we go. Darker, 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 darker. I deal with dark matter everyone. I gotta get up at 4 o'clock in the morning to go to work, right? This is how you deal with dark matter, right? There we go. You having a good time? Ma'am, you having a good time? Are you having a good time? Good, excellent, excellent. So the question tonight is, how do we deal not only with the discrepancies in the universe and the calculations that have to be made to account for this discrepancy, and the theories that abound about this discrepancy, but we're going to also deal with the fact that scientists are debating all various scenarios of what this could possibly be. We're going to talk about the process of discovering what dark matter actually could be. And there are some models. Take a deep breath. Deep breath. 80% of what you breathed is useless to you. It's sort of the dark matter of the atmosphere. It's called nitrogen, right? Doesn't interact with anything. It interacts with the soil. Every day, 80% of the atmosphere. You can't see it. Does nothing. Climatologists will dispute that, but it's sort of the same kind of thing, that it could be ubiquitous, a huge presence, but it doesn't particularly make itself known. So scientists have dealt with this in the past, and we have dealt with this in the past, and we have an unbelievable group of scientists here tonight to share their theories, to talk about their experimental results and the experimental results that they expect to get, to talk about just how on the edge this whole dark matter question is. And I was in the green room with these guys, and one of the great things about the World Science Festival, you get to hear these people talk in the language that they actually talk in. There was one point where Weiner was talking with McGaw, and they were, and Corey, and they were going back and forth about AMS and cross sections of the AMS. But that doesn't work unless you have a Sonnenfeld enhancement. And I want to find out what a Sonnenfeld enhancement is, because I think I need a Sonnenfeld enhancement. I'm looking pretty good, but at my age, I need everything. Let's welcome our fantastic panel here at this Shaking Up the Dark Universe session. First, Stacy McGaw from Case Western Reserve University. The man is missing game 1 of the NBA Finals, so it's a reason for another applause. He's chair of the Department of Astronomy at Case Western and director of the Warner and Swayze Observatory. Our next participant is an associate professor and undergraduate chair of physics and astronomy at the University of Pennsylvania. His research focuses on particle physics and cosmology and on new models of dark matter and dark energy. Please say hello to Justin Corey. The George E. Uhlenbeck Professor of Physics at the University of Michigan is our next guest. Visiting Professor of Physics at Stockholm University, she was the director of Nordita, the Nordic Institute for Theoretical Physics, and has a BOA. Ladies and gentlemen, Catherine Fries. Professor of Physics at NYU, right here in the neighborhood, director of the Center for Cosmology and Particle Physics. His research is primarily on physics beyond the standard model, including supersymmetry and grand unification. Neil Weiner. And we think of her as the superstar of dark energy. Our final guest is the Frank B. Baird Jr. Professor of Science at Harvard University. She currently studies particle physics and cosmology. Her current book, Dark Matter and the Dinosaurs, is one of 2 books she's had on the New York Times bestseller list. Please welcome Lisa Randall. All right, so you're the science guys and gals. I'm going to ask the question just straight out. Stacy, what is dark matter?
Well, we don't know, as the video said.
Oh, great. Helpful.
It is a failure of the mechanics that we know. If you apply the laws of motion as taught to us by Newton and Einstein to galaxies and then clusters of galaxies, they fail. There's a discrepancy.
It's a discrepancy. So dark matter represents a discrepancy. Justin, what do you think dark matter is?
So I think it is I believe it's a new particle. There's preponderance of evidence coming from the microwave background, from the evolution of galaxies and large-scale structure, that there is this dark particle, but I don't believe it is the simplest kind of particle that people think about. I think it's rather a particle that has new types of properties to explain the kind of things that we see in galaxies, namely MON, that we'll discuss.
One vote for cosmic screw-up, one vote for weird new particle. Catherine Fries, dark matter. What is dark matter?
Well, I'm going to tell you about the role it plays in the cosmic cocktail.
Okay.
So
which is your book.
Which is my book.
That's right, which is a fantastic book, by the way.
Oh, thank you.
Yes.
So the universe, what is it made of? So we have, let's make a drink with 10 ounces. So then we have a 1/100th of an ounce stars, 100th of an ounce neutrinos, 1/2 an ounce hydrogen and helium, and then almost 3 ounces dark matter, and then we have that 7 ounces of dark energy. So you put it all in a cocktail and you shake it in the early universe, and there you go. That's what the role dark matter plays.
So can a child under the age of 18 buy dark energy and dark matter?
It's going through you right now.
Yeah. Well, all right. That's the theory. You're a WIMP proponent, yes?
Yes. Yeah,
right.
I'm with Justin on the particles, but I'm going for the most simple, popular explanation. The WIMPs.
Neil, where do you stand?
I'm probably between the two of them. I think that dark matter, I think dark matter is probably a particle. I think it's out there. But the way I think about it is that the analogy I like to use is that if you had a professor who was made out of dark matter and they discovered that 4% of the universe were made out of something, and so you have some professor and she's coming up for tenure and she writes a paper explaining the 4% that we see, and she writes down the crazy theory of quantum chromodynamics and weak interactions and hypercharge and many generations and quarks and leptons. I mean, then people would say that's crazy, and then they would not give her tenure. But we apply similar, when we look at dark sector, we think that it should be a very, very simple thing, and I think that's probably wrong.
So the idea that dark matter is simple is wrong.
I think so.
The idea that you can be tenured and talk about dark matter, that's correct.
Yes.
Okay. All right. Lisa, where do you stand on this? Is there a short elevator pitch to what the dark matter is?
Yeah, but they probably would be wrong, going along the lines of what Neil just said. I mean, I think everyone wants to find a simple explanation to say it's one simple particle, but that is a very, very big assumption. And it's true, we know some properties of dark matter. We know it's very weakly interacting. We only know about its gravitational interactions at this point. It's also, we know it's matter. It clumps together. But what's really interesting, so I would say, you can ask that question to all of us, and we can all tell you what we think it is. But you shouldn't believe us. I mean, the real question is, how are we going to find out what it is? And how are we going to do those tests? And that's really the point of view that I try to emphasize, although I do also talk about many models, including these more complicated models with more than one type of particle. The really important thing is to say, how are we going to find out what that is?
No, and in fact, we're going to explore some of the detector strategies, some of the initiatives that are afoot theoretically in the course of this discussion, but I wanted to get a sense of, where people stand. I mean, is it the case, you said a moment ago, which is kind of interesting, all we know about dark matter is its gravitational interaction. Now, is that...
Well, we know more because we haven't seen the other interactions.
Right,
so actually, we know that it has gravitational, but we also know that it can't just be charged like other matter that we've seen.
Right.
So we actually know a lot.
Is the basis for knowing its gravitational properties simply the fact that it's, Ms. Rumid's discrepancy of galactic velocities, spinning velocities, that if the amount of mass that we see is not enough, dark matter would make up for it, therefore it must have gravity? Is that what we're saying? Is the gravitational interaction? So that's the discrepancy. So that the gravitational interaction isn't something we even really know. It's kind of...
Well, actually, if it's matter, that's what defines matter, is how it interacts via gravity. So actually, if it is matter, we do know its gravitational interaction.
Well, the question of what our assumptions are and what evidence we would have for any of this stuff is really the exploration and the puzzle that we have on our hand. Let's talk, Catherine, about WIMPs. What are WIMPs? I mean,
well, so it stands for weakly interacting massive particles. So,
and is there like a place where you come up with those acronyms, like a special committee or?
Well, oh God, I feel like saying it describes the person who came up with the name, but he would kill me.
Oh. So it's kind of like that. I love that. Yeah.
I should not.
That's good. That's good. Okay.
But,
all right. So they weakly interact, obviously,
yeah.
because we can't see them, but they do have some sort of gravitational.
So there are four fundamental forces of nature that we know about.
Yeah.
And so one of them is electromagnetism, and we know dark matter does not feel that force. It's not giving off light. And so, okay, it's not that. Strong interactions, we also know that dark matter doesn't participate in that, and that is the force that holds our nuclei together. Mm-hmm. So, yes, there's gravity, but then there is one left, and that is the weak nuclear force. And you can postulate that dark matter does feel the weak nuclear force, and that's what these WIMP particles are. That's what the WI stands for in the name. And if you make that assumption, then a lot of things come out right theoretically, so we kind of like it. So theoretically, it's a beautiful candidate. Now, as Lisa says, well, in this case, we are looking for it. And so, but and so there's a lot going on there.
Right. So to find something that interacts only through the weak force, we would have to blot out or get rid of a lot of other much stronger forces and phenomena in the galaxy. And so that's basically the detector strategy for trying to figure out if we can detect a WIMP actually interacting with matter. Is that fair to say?
The really funny thing about it is that even though it's called the weakly interacting massive particle, the reason everyone likes WIMPs is that they're the particles that actually would interact the most aside from gravity. Because even this weak interaction, and it wouldn't even necessarily even be full weak force strength, but even this little interaction that tells you it has a standard model force other than gravity means that we can find it with detectors that are made up of stuff that we know.
Right. So if it does satisfy the property of interacting through the weak force, a detector would actually detect it. So well, here,
there's three ways to look for it.
Let me run the video that just shows the detectors that we have, because we've got fabulous pictures and eye candy and all sorts of stuff. So let's see what some of these detectors look like, and we'll come back and talk about them.
Scientists have created devices sensitive enough to detect the impact of a dark matter particle should one strike a single atom in its sensor. Unfortunately, it's noisy here on the Earth's surface. We are bombarded by cosmic rays, and they do interact with regular matter, raining down a noisy shower that helps the detector, threatening to drown out what would be the quieter, almost completely silent impact from a dark matter particle. So scientists place these detectors where cosmic rays can't penetrate, far underground, in abandoned mines, and inside mountains. So far underground, there is no noise. Only then, when the atoms in the detector are nearly still, can scientists patiently wait for that almost imperceptible whisper of a dark matter particle strike. Detectors like Xenon and the Dama Libra work differently. They are made with atoms that will emit photons and sparkle with light if WIMPs strike them. Another method altogether is indirect detection. While dark matter doesn't give off light, the debris from two dark matter particles colliding might produce things we can detect, like gamma rays. The Fermi satellite has measured an excess coming from the direction of the center of our galaxy that may be caused by dark matter. Back on Earth, rather than waiting for dark matter particles to arrive from space, there's an experiment attempting to generate WIMPs from scratch by slamming protons together at nearly the speed of light. The violent head-on collisions convert this energy into showers of exotic particles scattering in all directions. Perhaps, within this debris, a short-lived dark matter particle will wink into existence.
Do you go along with all those, by the way?
That's a great video. I was going to talk about the 3 ways to detect it. There they are.
There they are. Well, is the first option, the deep in the mountains, deep in the mines, very quiet, isolating something away from all other forces, is that something like the LIGO experiment to detect gravity waves, where you've got something that on Earth is trying to detect something that's very, very difficult to detect, very, very sensitive, and so this, crazy kind of detector will, because that was successful.
Well, these experiments, they are very difficult. So the count rate is, if you have a kilogram of detector, then you're going to get, in a day, you might hope for 1 hit from one of these things, and you have to get rid of all the competing signals that there's a lot more of. And then the amount of energy that's deposited when there is a hit is really, really tiny, so you have to be really clever to find that this event ever took place. So it requires really great sensitivity. So these experimentalists are awesome.
So where do we stand in terms of, are they waiting? Are they still designing the software? Are the detectors sort of being optimized?
The slide shows that in the last 25 years, there's been an explosion of these detectors, and that's where they are. So they're all over the world, in all the different continents, including underneath the ice at the South Pole. And there's one, the Dama experiment, that's in Italy. It's underneath the Apennine Mountains. It's near Rome. And by the way, I think if you're going to be underground, I think the one near Rome is the place to be. But anyhow, and they have a signal. So they have this is an idea that we had in, well, I won't say when because it'll date me. But anyway, so the signals should go up and down with the time of year as the Earth moves around the sun. And that's exactly what they see. So they see more counts in June than they do in December. And they've got 10 years worth of cycles of this. So they're definitely seeing an annual modulation. But now the question is that from the dark matter or is that from something else? So, and it's strange. They won't let anybody see the data, so that's weird. And then other experiments don't see anything, that's weird. So what has to happen is the same experiment with the same detectors that takes place somewhere else. And that is going to happen, including underneath the ice at the South Pole. So there will be a check on these experiments very soon, in the next couple of years.
Yeah, I just wanted to emphasize how very, very sensitive these experiments have to be, because if the WIMP hypothesis is correct, there are of order a few hundred of these WIMPs passing through your body this instant. There are plenty of them in this room.
Actually, billions per second. Billions
Depends
per
on
second.
the mass, right? But lots.
No,
there are lots.
No,
we agree on lots.
Lots, billions per second.
But you only hope to count this 1 in a kilogram per day, because most of them just pass through without interacting at all. That's why we call it the weak force. It's very, very rare that it ever happens. Okay, and so that's the sort of signal that the experimenters are working for. And they've made fantastic progress in building these underground experiments and making more and more sensitive. And certainly over the past 25 years, or even over the past 10 years, they've increased their sensitivity by orders of magnitude. So they're really making great progress at what some of them call looking under the searchlight. Because as some people mentioned already, it's a good thing if they're weakly interacting, then we can actually hope to detect them, right? So we're looking for something that we should be able to detect in a detector, but it doesn't have to be that.
I know I'm asking the wrong person, but Neil, just a general reality check on what you feel about these detectors and whether they're a real test of the hypothesis.
What everybody says is correct. The most important thing to emphasize is just how clever the experimentalists have been. Mm-hmm. They've improved their sensitivity, I think, since I started graduate school by almost a factor of 1 billion in the strength of the interaction of dark matter and looking for it. And it's not even just as simple as that you put these things underground and you shield from cosmic rays, because that solves one of your problems, but then the rock is radioactive in the lab, and the experiment itself is actually radioactive. Mm-hmm. There are these sorts of things that they've learned to deal with that allows you to have a vat of 100 kilograms of xenon and let it sit there for a year and wait to see if a single nucleus gets kicked. And so that ends up being a very, very general purpose test of not just WIMPs, but a lot of different models that can end up with interactions. Because once you go over a factor of 1 billion in strength of interactions, you're not just probing the weak interactions, you're probing a lot of different strengths of interactions. So these are wonderful experiments. They're doing a great test for WIMPs, but they're testing a lot of things more broadly.
why the reference in the video to accelerating protons and crashing them into each other and expecting that maybe some weakly interacting particle that would be suspiciously a candidate for a WIMP would just sort of happen? Why would we believe that that was the case?
So we've talked a lot about WIMPs here, and why do people even think? I mean, it seems like a very optimistic assumption to think that the dark matter should be exactly the kind of particle we see. Okay, maybe it's not charged, but it interacts via forces we know. And so I should also be clear that just because we're all theorists here. That's why we all really admire the people who do the actual observations and experiments. Well, Stacy's an observer, and he's an astronomer. But none of us are actually. I mean, so what he does is also really impressive. Don't get me wrong. But I just want to be clear that if we're standing here having this admiration society for experimenters, it's because we're not doing it. But what we can do is we can say, what do you need in order to have dark matter work? So we were saying the things that we know about dark matter. Well, something we know about dark matter is how much energy it carries. And it carries 5 times the amount of energy as ordinary matter. And the question is, why is that? And so that's one of the few clues we have of what it should be. If it didn't interact with ordinary matter at all, that seems kind of mysterious. Why should it? I mean, for maybe a factor of 5 seems like a lot, but it could have been a quadrillion. It could have been 10 to the minus 15. It could have been a very different amount of energy. So if we find ideas that tell you the energy is comparable in dark matter and ordinary matter, that's maybe a clue. And the thing is, if a particle has mass about the same as the Higgs boson mass, which is what we studied at the Large Hadron Collider, that mass would, if you just followed the thermal evolution of the universe from the hot Big Bang to today, you would find that the amount of dark matter in the universe is just about right. The energy carried by that particle, as the universe cools down, there's less and less of it. But if you just work out how much gets left over, it seems about right. And that's one reason people have focused so much on that possibility. And the other reason is the one we've all been talking about, which is that it's maybe something you could actually make in a lab or detect in the laboratory. And if it really is related to the Higgs boson somehow, maybe you can make it at the Large Hadron Collider. It has the right mass. Maybe it's something that's there in some natural extension of what would produce the Higgs boson.
Well, and the flip side to what Lisa's saying is that there are a lot of very good theoretical motivations to believe there should be new particles that have mass in this range. The fact that you found a Higgs boson completes the standard model, but it brings with it a lot of theoretical problems. It's a very, very, very awkward theory, and it suggests we can work with it, but it's a very, very incomplete theory, and it suggests to us, based on our intuition, our understanding of how field theories work, that there should be a lot of stuff. And so if there is new stuff, and if it has a mass around the Higgs boson, and you just ask how much of it is left, you end up with approximately the mass, or the amount of stuff.
But I think
but let me just for the benefit of the audience members who are more like me than like our panel, and so we think the Higgs boson is relevant because it is a huge particle, and what we're looking for here in these WIMPs is sort of on the scale of the Higgs boson, and so we've had success finding the Higgs boson, so maybe we would have similar kind of success, but getting the Higgs boson to fit into some sort of pantheon with these dark matter particles would be a real challenge, you're saying?
Well, what I'm saying is that the standard model, it looks incomplete. It looks like there should be new things there. And if you ask what mass should those things have, their mass should be about that of the Higgs boson.
Right.
And then you do what Lisa said, you say, well, let me forget about any model. I don't have to pick my favorite model, just ask if one of those things were stable, how much would be left around? And the answer is about as much as we see.
So that's a fairly happy set of data points there. Let's talk for just 1 second about a couple other things that were in that video. Can we get some information about the gamma rays and the Fermi satellite and some of the other detections for possible dark matter that's from observable phenomena in the universe? Stacy?
So if WIMPs are the correct thing, they are their own antiparticle, and when they collide in space, they have a cascade of things that can result in the production of standard model particles. When we say standard model, we mean protons and neutrons and electrons and the things we all know about. And so one could hope to see the evidence for the existence of these kinds of things in space by cosmic rays that were emitted in this process, or gamma rays, as you mentioned. One of the things that would be really convincing to me is if you could map the gamma ray sky well enough that you not only saw this, but it looked like our simulations predict it should look like, and you see the dark matter halo in the emission of gamma rays, not just for our own Milky Way, but also the subhalos that are predicted to exist containing dwarf galaxies and so forth.
So what's the Fermi bubble that is predicted for our galaxy?
So the Fermi satellite is mapping the gamma ray sky.
Right.
And, well, the Fermi bubbles are these giant things that, well, here's the plane of the Milky Way.
Right.
Then these giant things that are 50,000 light years in extent that are seen in the gamma ray. Now, most of that is interesting astrophysics, but it's not dark matter. But near the center, there's a small spherical region that has an excess of these high-energy photons, these gamma rays, that we don't understand. So there are the sources that we do know wouldn't predict that you would see as much as you do towards the center of the galaxy. So then the thinking is, okay, well, we do know the center of the galaxy has a lot of dark matter, and so enough that there's dark matter annihilation still going on, and if it's WIMPs, the annihilation could produce those gamma rays, and that's what the Fermi satellite might be observing. So that's one of the hints that possibilities of detection. But
Jared,
it's really hard to tell. Is it some interesting astrophysics going on that has nothing to do with dark matter? Is it some other kind of sources that also could match the data, or is it really from dark matter? That's a tough one.
to explain very briefly gravitational lensing and how that is an attempt to take advantage of the apparent gravitational properties of dark matter and try to observe something.
Yeah, so that's a method. It's something completely different from what we've been talking about that also allows us to map out where dark matter is. What happens is that if you, whatever the mass is, it doesn't shine itself, but what it does is it affects any light behind the dark matter. So the light that's behind the dark matter gets bent on its way towards us. This is actually one of the predictions of Einstein's general relativity. And it was observed that the fact that this happens was observed, I think, in 1917 or something. It's known to be true that mass bends light. And so you can use that. You can observe, you say, okay, so if I look over here, it looks like there's a source over there, but it got bent this way, but then it also got bent that way. So you might see the identical object, multiple images of the same thing, and they're kind of sheared and weird looking. So by looking at these background images, that tells you about the mass that's intervening, that's on the way between the distant objects and you. So you can learn where dark matter is.
Kind of a nudge that it's giving in terms of being behind it or near it. You're detecting something that is an interaction, not actually directly observing dark matter.
It's not an interaction. It's actually just, it's gravity. It's space-time. It's the warping of space-time is one way to look at it.
I'm seeing the whole universe as a closet. And there are clothes in the closet, and there are clothes hangers in the closet. And for
well,
eons...
for God's sake, turn the light on.
For eons, no, it's a very dark closet. It's a dark closet. And for years, we've thought that we were the most important thing in the universe, and what we discover is, no, in fact, all we are the coat hangers. And there's this huge, dark mass that actually is much more significant and is actually the entire point of the entire universe, but we can't see it, and all we can detect is that there's something bending the coat hangers. If we could detect the bending of the coat hangers, we've got dark energy. Is that sort of...
Sure.
You like that? It's the title of my new book.
We see the coat hangers are bent, so we infer that the dark stuff is there.
As an astronomer, how frustrated do some of these models get you, Stacy?
A lot. I guess, there is a hysteresis to this. I learned cosmology an embarrassingly long time ago now, and there were many things that we thought had to be true in the context of cosmology. And one by one, those things have fallen by the wayside. And so I'm very jaded at this point about believing any of these models until I have something, very substantial. So what I'd say, observationally, it's very clear there is a discrepancy. It's very, very clear from the astronomical evidence that something is wrong. We need something. It could be dark matter. It could be something changing the mechanics. But that much is very clear. But what it is, I think we're still at sea about.
And this is basically what you look like when you're really frustrated and jaded?
Jaded, yeah.
Jaded, yeah. Okay. Justin, how about you? I mean, you're in a different realm and have taken a different sort of look at all of this. Do you find the collective groupthink about dark energy a little bit frustrating at this point in physics?
Yeah, a little bit. So I think with respect to, we just talked about gravitational lensing. So I think, to me, if we were to say there's no dark matter and instead it's a different law of gravity that's explaining the discrepancy, I think the gravitational lensing is the one piece that makes it very hard to accommodate such a different theory of gravity. Because as Katie said, Einstein predicts that if I have mass there in the form of dark matter, it will make ordinary matter rotate in a particular way, and it's also going to make light bend in a particular way. And with galaxy clusters, in particular, as the animation shows, we see this agreement. So that's convincing. But when we get to galaxies, my personal frustration is that in WIMP theories, we're not explaining the sort of conspiracies that Stacy has spent his career pointing out, that there's something very strange happening in galaxies. They should not have the properties that we observe them to have if dark matter were as simple as a WIMP, at least in my opinion. And people that believe in WIMPs, they have to believe in some kind of miracle involving the complicated physics of stars, star formation, energy released from complicated physics, and so that's what leaves me a little bit suspicious.
So, get into it here. I see that expression on your face.
What are you talking about?
He's talking about Tully Fisher.
Oh.
Yeah, Tully Fisher, there's the Tully Fisher, there are all these kinds of scaling relations. That,
So what he's talking about are there are various relationships.
You're just going to start here, guys.
Yeah, it's starting.
Okay, go ahead.
So when you look at the rotational properties of these galaxies and you compare the luminosity and as they're rotating, there seems to be this conspiracy, if you talk about just dark matter, over many, many scales, that there's a relationship that is something that you can't predict, that seems to work very, very well. And if you're a dark matter proponent, then what you say is, well, there's some complicated physics that somehow ends up with that simple law. And we need to understand it, but somehow all the physics will come together to give us that once we figure it out. And if you are, but you can come out from the other side and say, no, that is telling us that there's something deep that we need to understand. And these are things that Stacy and Justin have really been promoting, that this is something that maybe we really do need to focus on, and maybe we do need to understand.
So you want to take apart Newton and Einstein to basically try to get your head around this problem, right?
I don't want to take them apart, but I do want to consider the possibility that there's more to the story. Right? So Einstein's theory contains Newton, right? For a long time, Newtonian gravity was sufficient to explain what we understood in the solar system. Einstein came along and said, no, there's more to the story. And so we see here the orbits of the planets around the stars. This is orderly. You can see the innermost planets going around faster, the ones further out going more slowly. It's this orbital mechanics that lays at the foundation of much of this physics. This is what Newton explained. And the acceleration varies as you go further and further out. And the thing that I noticed that in my own work that I had not expected was that the discrepancy, that is, where you infer the need for dark matter, depends on a particular physical scale. That physical scale happens to be an acceleration, or the way I used to think of it was a surface density. Those are related in Newtonian gravity. And it was only when you got to extraordinarily low accelerations, about 1 part in 10 to the 11th of what we feel sitting in this room, that you start to see something go amiss. Above that, like in the solar system, Newton suffices, Einstein suffices, everything is fine. But there is this one magic scale where everything starts to break down. And so it sort of suggested to me that there might be something in the organization of the mechanics that was like this. So
let's which scale are you talking about? Really huge or really slow or really fast or what?
Really tiny and really tiny acceleration. So not just slow, it could be slow or fast, but acceleration, of course, is the rate of change of speed.
Okay.
And so standing on the surface of the Earth, we of course feel 1g, about 10 meters per second of acceleration. That's what we're used to. Where this happens is about 10 to the minus 10 meters per second. So it's a tiny, tiny acceleration, and yet it's that acceleration that is sufficient to hold stars in their orbits around galaxies.
So you're saying that a change in the properties of motion at a particular acceleration scale could account for the mathematical discrepancy of the rotation of the galaxies if it was sort of incrementally added up to make it, explain what Ms. Rubin saw.
So indeed, I would say empirically, that's just true. Theoretically, there already existed a theory, not mine, but by the Israeli physicist Moti Milgram, who suggested that, geez, we have this missing mass problem, maybe we shouldn't add dark matter, maybe we should tweak the force law. And many people tried to do that, many people failed, but he said, well, maybe it's not that galaxies are big in size that matters, it's that the accelerations are so tiny. And that's the idea that seems to have some merit to it.
Yeah. Well, I think that part of the reason that people like me are as adamant that dark matter is the explanation, probably at the end of the day, even though I think that the questions are critical, and I think that the studies they're doing are very, very important, is that the first thing is that it's conventional. It's it's the simplest idea is that there's something out there that we can't see. We already know there's neutrinos out there we can't see. The idea there's something else is a very, very, very unremarkable idea, fundamentally. It sounds cool, but really, stuff that we can't see, sure. The second is that when we talk about modifying the dynamics and calling that a theory gets a little bit tricky, because what Stacy's going to call theory and what I'm going to call theory are going to be somewhat different. And the rules of how you write down a theory, a consistent theory, is challenging. And so modifying a force law is a reasonable thing to do as a sort of a test of something. But writing down a real theory that can do that has challenged a lot of incredibly smart people. And so far, I would say that I don't think that there's one that is fully satisfactory without some additional dark matter in it. And of course, Justin's done a tremendous amount of work, and I'm not sure that I'm convinced that he solved it either, but he's done a tremendous amount of work recently trying to develop precisely such a theory, but it's a very hard thing to do.
Well, let's look at your observable evidence of the Milgram formula for modified Newtonian dynamics. You seem to think that ways in which certain galaxies behave at low luminosity might suggest that there's a dark matter interaction there, or it explains the discrepancy.
Well, indeed. So, I came at this from exactly the conventional point of view that Katie was advocating. There's dark matter, it's some non-normal matter, probably a WIMP. And I had my own ideas about what that might do, but that wasn't important. What I was interested in was observations of these low surface brightness galaxies. When I started doing this work, not much was known about them. And so you can see an example. Low surface brightness galaxies are just normal galaxies where the stars and the gas are spread very thin. It means there's a low surface density of mass. Okay? And that turns out to be related to this acceleration that I mentioned earlier.
So these are mellow galaxies.
They're very laid back.
They're like Williamsburg. They're like Williamsburg in Brooklyn. Yeah.
And they're slow rotators. They're very diffuse, slow things going on. And so I had an expectation, my own prediction for what they should do in terms of dark matter, and they did not do that. And so I started looking at other theories. And that's a very hard thing for a scientist to admit, right? I had the theory. It predicted one thing right. It predicted another thing wrong. So I started looking at other people's theories, and they could get the thing right that I got wrong, but they got wrong the thing I got right. Right? And so I kept looking.
I was really feeling for you there for a moment, and then I kind of went right off the pool edge there.
Well, so to cut it short, the one theory that predicted what I was seeing was this crazy theory of Milgram's. And I remember reading his paper, which I had just ignored for a long time, but finding in it a statement that low surface brightness galaxies should have low acceleration, so they should do this series of specific things. And he'd written that 10 years before I did the experiment, right? And so I thought, well, Great, I've got the data to disprove this stupid theory. And I went through his predictions. Yeah, they do that. Yeah, they do that. Yeah, they do that. All of them came true in the data. So what am I supposed to say? He's wrong? Now, there are lots of other things in the universe than low surface brightness galaxies. So I spent a lot of my time fact-checking and going through it. And basically, there were two things that I found. There was the kind that Mon just said nothing about and couldn't explain. And there was the kind that, well, yeah, that works pretty well. And this happened over and over and over. So it really convinced me that I was wrong to have been so sure that it had to be dark matter, and it couldn't be some more general problem of mechanics.
So,
Can
what
I
do
chime
you,
in
go ahead,
something?
Justin.
So I think it's important for our discussion to distinguish between theory and empirical facts. So to me, the Milgram idea that Stacy is talking about is not per se a theory, but it's an empirical fact about galaxies. So even if we believe dark matter exists in the most conventional way and it's just Einstein gravity, Milgram's empirical statement about this low acceleration scale is there in the data. So at the end of the day, when you put it all in, all the baryon stuff, all the crazy
It's
physics,
sort of a Kepler's law.
it has to come out.
galaxies.
It has to come out, okay? So where we disagree maybe is whether it's actually a fundamental statement about gravity, whether it's actually some complicated star physics, or whether it's actually something about dark matter itself. I think that's, but we have to distinguish between theory and empirical statements, I think.
Could this all come back to we don't fully understand how gravity behaves and that it could in fact be granular in the way that it operates throughout the universe instead of absolutely equivalent everywhere in the universe as Einstein insisted it must?
So I think that's a question of scale, and probably on these scales, we really do trust gravity. I mean, there might be very tiny scales where far beyond anything we can observe at this point, where ideas can break down and all sorts of cool theories come into play. But right now, we're at scales where we do trust. So the only thing that I would really take issue with a little bit is, when we say the predictions of dark matter, because we can predict from a particular model of dark matter, taking into account certain phenomena. So it could be that the predictions of dark matter are very different either because we haven't yet fully accounted for what ordinary matter does, or even more interestingly, maybe dark matter has some properties we haven't yet thought about. And I think that's a lot the kind of work that Neil and I do, is try to think, what are alternatives to the standard dark matter picture? That when you see these anomalies, could they be accounted for by dark matter? And one of the things the anomalies do sometimes is suggest new types of dark matter that have been ignored before. I mean, it's very easy to sort of say, we like WIMPs. And we like WIMPs in part because, we can look for them because they interact with ordinary stuff. But there's also really subtle ways that new types of dark matter might show itself in the way matter organizes. Maybe the gravitational forces, even when we measure gravitational forces, we'll see the distribution of matter looks different than we anticipated. And that could be a really interesting insight into what maybe dark matter has properties other than the ones we originally assumed.
Oh, okay, so Catherine, this is the point at which you can maybe cast a little doubt on Stacy's epiphany about it can't be WIMPs because of what I observed.
We know something about dark matter, not just the way it's pulling things around today, but also the role that it played in the early universe. So in fact, without dark matter, we would not exist. We need dark matter to start clumping together early on to make galaxies. And then later on, it's then the ordinary matter that falls into these dark matter objects. And so I see the cosmic microwave background is now on the screen. And what that is, that's the relic leftover light from the hot early phase of the universe. And it tells us about dark matter. So in fact, if you take all those blue spots, those are cold spots in the microwave background, stack them together. And so you get one big blue spot. And then you take the hot spots, the red spots, and you stack them together. What you're going to see is that the blue spots, that's the dark matter. That's the gravitational potential that's pulling in everything else. And the oscillations from the early universe leave the baryons and the photons farther out. And so this is these dark, attractive regions that make the galaxies first. These are screaming evidence for dark matter. And this is something that Mond really struggles with, is to actually match the amount of data in this picture is what it tells us about the cosmology of the universe is just mind-boggling. Precision, accuracy, including on the amount of dark matter. And this is something that all the existing theories for well, I won't say MON, but for like TEVIS is a particular variant, which it's a well-defined theory. It doesn't match the microwave background. It won't give you a picture like that. So I think that's a deep problem with, it may match observations on galactic scales, but it's not cutting it.
You think that bullet clusters also dispute the Newtonian dynamics?
Yeah, that's another one. So this is one problem. The other one is going back to the very first image when we first sat down. That is the bullet cluster, and here's a video of it. So what we think is going on here is the two clusters are merging together, and we call it a bullet because one of them, it looks like a bullet. And what happens when these clusters merge is that you see evidence for two separate types of mass. So the stuff that is shown in pink, that's the gas. So when these clusters collide, the gas gets stuck. It's as though you and I collide, well, we're going to get stuck because we have electromagnetic interactions, we have strong interactions, we're not going very far. But it looks like there's a second component that's shown in blue where the mass just keeps going. I mean, it has gravity, and so it'll eventually come back, but it just kept going. And so there's a split in the behavior of these two types of mass. And by the way, the way you see the blue stuff, again, is using lensing. So this is, to my mind, pretty firm evidence that you've actually got two types of mass out there. So the ordinary stuff and then the dark stuff.
Is it correct to say two types of mass, or do you have to say two types of matter?
Okay, two types of matter.
But they're the same thing? They're equivalent?
I should have been careful. Two types of matter.
Okay, I'm ignorant, believe me. But I just, two types of mass, I'm thinking, okay, I'll have to go home and, Google that kind of thing.
That's what those guys think. There's two types of mass.
Well, so, I mean, the bullet cluster, I think, is good evidence against both dark matter and the standard cosmology. You saw that collision video. These things collide too fast to explain in the conventional picture, or at least that's what we initially thought. That fast collision speed is quite natural to MOND. And since then, we've come up with a story for how that could happen in the conventional dark matter picture. There's a sociological issue here. We accept that story because it's what we want to hear. It's accepted uncritically. MOND never gets that thing. So if I put on my dark matter hat, I say, yes, there has to be dark matter there. If I put on my MOND hat, I say, well, okay, this is a problem for all clusters, not just the bullet cluster. There's more mass there than meets the eye. That's terrible for a theory like MOND that's trying to do away with dark matter. On the other hand,
you could just go to clubs where there's all MOND people.
I'm worried that we're starting to fission into different groups that way. But there's something worse that we haven't told you yet. When we say dark matter, usually what we mean is something like a WIMP, something entirely novel that's not in our standard model of particle physics. But we also have a pretty good idea of how much normal matter there should be in the universe from the abundance of light elements and how they were synthesized in the early universe. If astronomers go out and add up the gas and the stars and the stuff that we see, we do not have a complete census of that. So there's also dark normal matter. In addition to the unseen missing mass, it's something totally else. There's also unseen baryons. So if I ask, baryons is the scientific word for normal matter, protons, neutrons, stuff like that. So if I ask how much of that is missing and how much I need to fix this problem in MOND, it's no problem. The sum is there. We know, all of us agree, that there's enough normal matter out there to fix this problem. The hard part is actually building a satisfactory model that explains these data.
When you say satisfactory model, you mean a model that doesn't ditch the rest of physics for the last 100 years, right?
Well, in this specific case, I actually mean where would you hide that much normal matter in that kind of galaxy? Because as Katie pointed out, most of the mass has gone through. The gas has stuck, and most of the mass that's unseen is going to be. So it has to be something that's normal matter, but also is in some kind of dense thing like a very faint star that would just run past each other without colliding.
Well, I mean, we spent, as far as I know, astronomers had jobs even before we could see anything other than the moon and a few stars. So the idea that things could be hidden from us is not completely outrageous. We don't have the best view of the universe.
Can I just take one exception to one thing Stacy said?
Okay, sure.
He said this is what people want to hear. And I want to take exception to that, because I would love it if Einstein's gravity were wrong. That would be such a fantastic, interesting thing. I could spend the rest of my career studying that. It would be amazing. So when you say what I want to hear, I would love for that to be right. But I think the conventional explanation of dark matter is the simpler one to go with for right now. And, as Justin pointed out, the empirical relationship does not constitute a theory. And to say that you can explain all of these data, well, there's not necessarily a complete theory that you can take all the way back to the early universe and move forward. Okay, sorry, Justin, didn't mean to interrupt.
Justin, you have been looking at real structures here and possibilities for what dark matter might consist of. Explain.
Yeah, so I've been working on this theory in which dark matter actually forms a superfluid state. So a superfluid, I don't know if we have maybe an animation of that, but so we know of superfluids in the laboratory. The most famous example is liquid helium, and it's to my opinion, the most striking manifestation of quantum mechanics. When you take liquid helium and you cool it down at sufficiently low temperature, what happens is instead of forming a solid, like normal fluids would, it stays a fluid all the way to absolute zero temperature. And this may, so here we see the animation. So you see at high enough temperature, it's bubbling, 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 and then you bring it down to the critical temperature, and all of a sudden its manifestation becomes completely different. And that is quantum mechanics. Now, at this point, the superfluid state is reached, and the helium atoms are no longer functioning as individual, independent entities, but they're really in unison. And so now you might think, okay, why would I think that dark matter is this crazy type of stuff? Well, the first thing to say is that it's not that crazy. All you need to have a superfluid state, people do it with atoms in the laboratory, you need two things. You need to have a lot of these guys, a lot of atoms, densely packed, and you need very cold temperatures. And dark matter, not the WIMPs, but some other form of dark matter can satisfy both those things. And the idea that I had is that if dark matter forms a superfluid, then as we said, they no longer behave like these individually moving, randomly moving particles. They behave coherently in unison. And what the theory we developed is that, in particular, one of the excitations that the superfluid can have are sound waves, phonons, the same kind of sound waves that allow you to hear me. And those sound waves could mediate the type of force that Stacy is talking about. So, of course, it's a speculative idea, but it does combine, on the one hand, the successes of dark matter for the cosmic microwave background and large-scale structure, while attempting to explain the properties of galaxies that Stacy was talking about within some unified framework.
Wouldn't a superfluid, though, in places in the universe where there is high energy, wouldn't it condense and show itself in some way?
So very nice. So maybe I can address this cluster story, because that's very nice. So it also explains, so one thing that Stacy mentioned was, okay, this Milgram formula works well in galaxies, and what happens with bullet clusters, and what happens in galaxy clusters. So one thing that is special to galaxy clusters is that they're very massive, and as a result, dark matter particles in them would be moving around much faster. And what that would mean from the point of view of a superfluid is that, in fact, they're moving so fast that their energy, their kinetic energy, is such that they're above the transition. So they're behaving really like normal particles as opposed to superfluid. So that's one way in the model in which you distinguish between large objects like clusters and galaxies.
So they sneakily become ordinary mass without...
They become sneakily ordinary, and they become, for a reason I won't get into, but they also sneakily become ordinary in the solar system, where you don't necessarily want to mess around with ordinary gravity.
All right. So dark matter is actually sneaky matter.
It is sneaky matter.
Yeah, a sneaky superfluid. Sneaky superfluid. Is there any sort of theory that suggests the kinds of behavior that you're talking about that you're relying on here, or?
Yeah, very good. So the real motivation for me for thinking about this was that mathematically, when you write down the theory that describes those sound waves, it looks eerily similar, strikingly similar mathematically to theories of superfluids that we know. Okay, so it's really a mathematical analogy. And when you get these theories that mathematically look the same, you say, gee, maybe, actually what I'm describing is, maybe this theory is describing a superfluid. So it's really an analogy with ordinary systems that we've studied in the laboratory.
What would you have to observe, Neil, in the universe to become close to confirming what Justin is talking about here?
That's a good question. I think that I'm a big fan of the paper. I mean, of the papers. I think it's a really, really interesting idea.
The paper that it was written on, or the
work, Justin's work. I think it's a really interesting idea. The idea, we look at ordinary matter takes on all sorts of different forms and phases, and so the idea that dark matter might do that, and you should think about the consequences is the right thing to be thinking about. But we've also tested a lot of things about dark matter, and so what I would want to see is that as you study the systems, that it's not just a description, but it can make predictions of other systems that you can look for and things that you can measure. And if Justin can do that for me, then I would start believing him.
Can you test it in a lab? This kind of superfluids that we already have?
That's what we're hoping, yeah.
That would be really cool.
Indeed, that's the ultimate dream, to find an actual, so cold atoms is what people study, right? Yeah. So we would want, it's a cold atom that looks like a cold atom system that we know of, but not quite. So if we could find such a system, then the dream is to test galaxy collisions and stuff in the laboratory. You know, we're theorists, so we dream and we get excited. Yeah. So now I'm excited about this. In a year's time, I'd be excited about something else.
Yeah, but can you get paid?
Maybe in 6 months.
Yeah, can you get paid for being dreamy and excited?
Yes.
That's the key. I mean, does science support all of the initiatives that are looking at dark matter, or does science right now favor a particular set of assumptions and initiatives?
Well, as the field progresses, there are a lot of R&D activities that go on, and at a small scale, oftentimes they can be done. There's an experiment, for instance, called DOMIC, which uses semiconductors to look for very, very light dark matter, and it's a really interesting experiment.
It's cheap. What a great idea.
It's a fantastic idea. But when you scale it up to the ton level, like xenon or CDMS, these are these experiments that use a ton of material, things get expensive, and you just can't do every experiment at that level. And so there's a process to do these things. But the thing to remember is that, we're working on these things because we're optimistic about the ability to discover them. But with the Higgs boson, that was a particle where you knew exactly its properties up to one unknown parameter, its mass, and it took you 50 years to find it. Mm-hmm. And dark matter, we don't know what it is. There's no reason why we should think we'll be able to find it any faster.
In a lot of the theoretical discussions that led up to the discovery of the Higgs boson, there was a lot of talk about the beginning of the universe and how the various properties and particles that we were looking for were represented by particular states after the Big Bang. Is that helpful here, Catherine? I mean, is the idea that we can understand better dark matter by thinking about what its role? You mentioned the cosmic background radiation earlier. What is it about what we know about the early universe that would demand that dark matter be there, or that would theoretically assume that there must be some unaccounted for phenomenon that this far out would lead us to have things behave the way they are now?
Initially it was one object, it was actually in the 1930s, that people noticed, looking at a cluster of galaxies, that some of those galaxies were moving too fast. And so there was one type of observation that led to these, and then later on, Rubin and Inside Galaxies saw the same thing. But at this point, we have, I don't know how many different observations in cosmology, and they're pointing to a consensus picture that really does not work without something, either dark matter or something that sure as hell imitates it. So theoretically speaking, we needed it for the formation of galaxies, but you couldn't have done it because photons were moving out of early objects, and they pulled ordinary matter along with. So you needed dark matter to form the galaxies in the first place. But simply on the observational side, if you put all the different pieces together, the supernova measurements, clusters, cosmic microwave background, structure, how many galaxies we have of what mass, and so on, you put that all together, that consensus picture it's really very incredible accuracy. We know that dark matter is there at around 25%. And they argue, is it 24 or is it 26? But it is. It really is a quarter of the universe.
Is dark matter uniformly distributed in the universe? Is that a consensus?
Oh, absolutely not.
Absolutely not.
No. The dark energy, but not dark matter. No.
What would be the configuration of I mean, we sort of understand why ordinary matter, condensed into gravities and or galaxies and planets and solar systems and that sort of thing. What is going on with the dark matter, and then how does dark energy add to this picture?
Well, dark matter, you painted that beautifully. It starts out by making small objects like Earth mass objects. They then merge together to make bigger objects. Eventually, you get galaxies, which are today merging together to make clusters and superclusters and long filaments of structure. So we see these things, when we look in the sky, you can see these things by looking at the stars that are inside them.
But it's not some Star Trek kind of dark. There are dark planets and dark galaxies and dark.
There could be.
There could be.
We don't know yet.
Oh, there definitely could be. We think there probably are.
I mean, we wouldn't. Well, there's certainly theories that you can write down where that would be true, but we haven't seen them yet precisely because it's not even clear if there were these dark people, this untenured person, if they would know that we have planets. They don't see all our matter. So, in fact, we don't see, it took us a long time to see a lot of the asteroids out there, and we're still looking for them. And so these dark people that don't even see these same forces, I mean, it's not that surprising that there should be a lot of stuff we don't see, because we need significant interactions.
Would the hidden dimensions in string theory assist in accounting for the way dark matter?
Look, there's so many possible explanations for what dark matter, and it sounds really cool, like that, a lot of people like to think, oh, string theory, black holes, all the extra dimensions, they all must have a role, and they probably do all have a role, but that doesn't mean they all have a role at once. I mean, we're trying to really break it down to see, I mean, in some ways, I've worked on extra dimensions, I think it's very cool, but I think it's much better to sort of focus on what are the phenomena about our universe, and that's a very different scale we're looking at. And I think what everyone was sort of hinting at is, both two things. I mean, one, dark matter is really hard to find, and two, there's a lot of data out there. And so we want to be in the best position possible to exploit all of that. It's really interesting. In this new type of dark matter that we've been thinking about, it has astronomical implications. And a lot of astronomers, their sort of point of view, I mean, Stacy's different in the sense that a lot of the point of view is sort of, can we fit what we have? But from a particle physics point of view, we want to know what are the possibilities that are allowed by what we've seen. What could be out there? And if there is something new, what would we look for? So we're going to look for that in the cosmic microwave background. We're going to look for that in detectors that we have on Earth. We're going to look for it in various astronomical measurements that have these large data sets now, where we're measuring the details of the Milky Way galaxy, 1 billion stars in the Milky Way galaxy. Maybe their distribution won't be what we expect. Maybe that will tell us something about dark matter. There's lots of possibilities that we haven't yet thought about as telling us information about dark matter, but now that we know they're there, it makes sense for us as model builders to think, what are the possibilities and what kind of predictions would they make?
What would the mind-blowing headline be in the sort of search for dark matter? Is it, we found it? Is it, there's a whole parallel set of properties of matter here that have this whole other sort of way of behaving? Is it everything we know is wrong? What's the kind of headline that's going to...
I'm just going to say one quick thing. So it was really interesting to see what the quick headline was when LIGO discovered something. So it discovered gravity waves. What it really saw was black holes that were merging. But a lot of the ways it was advertised was Einstein was right. I mean, that's in some ways the least interesting thing. We knew Einstein was right. But, so how things get advertised isn't necessarily what we as physicists think is the most exciting thing about it. But I'll say that anything they find about dark matter will be a great headline, as far as I'm concerned.
Neil?
Now, there's another funny, interesting candidate for dark matter. What if those black holes that merged together, and that's what gave the gravitational waves that LIGO found, what if those are dark matter? So the dark matter could be primordial black holes that were formed very, very early in the universe. You were asking about the early universe. Okay, these would be way, way back. And there could be lots of those in our galaxy, and maybe 2 of those gave rise to these gravitational waves.
So detecting dark matter would be finding these primordial black holes that are made of dark matter and detecting their collision.
The dark matter is made of primordial black holes. That's what it is. So.
How many primordial black holes does it take to make a universe?
To make a universe?
25%.
Infinite.
Infinite, yes. Very good. Neil, you still haven't answered. What would be the headline that would...
Well, I mean, if it depends on how you find it. I mean, I think something, as Lisa's talking about, all the different models and ideas that people have for dark matter, it's not just an exercise in coming up with models we like. One of the important things is that since you don't know what dark matter is, a priori you don't know how to find it until you have a model. And then once you have that model, then you can say, okay, this is how you can look for it. If I have a vat of liquid xenon, I don't know that a nuclear recoil is a sign of dark matter, except for that it turns out that it is because of these particular models. But
what is the nuclear recoil?
Oh, a nucleus getting smacked by dark matter. So you've got a big vat of liquid xenon, it's sitting there, eventually dark matter comes in, knocks it, like in the movie. But if I didn't have a model of dark matter, I don't know why that is something I should look for. So if we don't have the models of dark matter, we can't even start talking about how to look for it. And so if you find it, the first question is, well, how did you find it? And then, is that the dark matter or just some of the dark matter? Because, like I said, we already know that there's two types of dark matter, the two neutrinos at least that have mass, maybe three. If you find dark matter,
everybody believe neutrinos are dark matter?
Well, they are part of the dark matter.
Well, sterile neutrinos could be.
No. I mean, I just mean active neutrinos are a tiny, tiny, tiny fraction of dark matter. They're dark. They have mass. That's dark matter.
Just not enough.
It's just not enough.
Exactly.
It's just not enough. Yes. But I'm just saying that it shouldn't surprise us that there are then other things. But I think the story actually begins once you find it, because now you know you're looking in the right place.
What would you, Justin, love to see as a clarifier in terms
So
of...
for me, a headline would actually be a theoretical idea. I think empirically we know a lot about dark matter, we know a lot about dark energy. What we're missing is a great theoretical idea for what the whole dark sector is all about. I think what Lisa said about Einstein was great. I think at the time there were some empirical discrepancies with Mercury's orbit and so forth, and when he came up with general relativity, you look at this and you say, oh yes, this has to be true because it's so beautiful. And I think now that's what's missing. We don't have a beautiful, holistic explanation of what dark energy and dark matter are together as a dark sector.
Especially dark energy.
Yeah. But together, it would be wonderful to have a theory that somehow brings them together in some elegant way.
Stacey, correct me if I'm wrong, but it sounds like the mind-blowing headline in your point of view at this point in time would be, we fixed their math.
Well, it would be great to find a unifying theory in the same sense that Justin just said, and I think it's important to keep a broad open mind as to what that could look like, and it may be that it's something like Justin's dark matter, something like MOND, that there is some combined greater thing that we have yet to imagine that explains all these things simultaneously. But to me, the mind-blowing thing would if we actually detect it in the underground labs, if we see it in the gamma rays, if the LHC actually produces a dark matter-like particle. But the counterpoint to that is, what if we never see it? When do we decide that we're wrong?
Is that more or less likely than the Cavaliers winning the finals? You don't want to.
I think I got to give Cavs the better odds.
Confidence in the Warriors. Wow.
Final thoughts on all of this. This has been a fascinating discussion. What are, first of all, Sonnenheim enhancements before I go?
Sommerfeld.
You talked about that downstairs, and I just kind of
Sommerfeld enhancements. Sommerfeld enhancements.
Sommerfeld enhancements.
This was a technical point that we were arguing about downstairs.
See, it's so much fun downstairs.
It's that when one point that Stacey made is that when you talk, and that Lisa made, which is that theorists say, oh, this is how dark matter acts, this is how dark matter acts, this is how dark matter usually acts. And that's always true until we come up with the new class of theories where it doesn't act like that at all. And Sommerfeld enhancements was something that became discussed quite a bit of late when we thought we knew how WIMPs and WIMP-like particles would have their collisions with each other. They shouldn't be too big, and then all of a sudden we said, oh, actually, that was wrong.
Because the Sommerfeld enhancement.
The Sommerfeld enhancement. It's just the idea that if you have dark matter particles, you usually think that they just kind of come together and they smack into each other. But what we didn't spend enough time thinking about is that as they came together, they might pull on each other, and then they would come and pull together and smack into each other more. In the same sense that if I throw a rock at the Earth, the probability of hitting the Earth, I don't have to throw it right at the Earth, right? I can throw it that way, and it'll still hit the Earth.
Sounds like swing dancing.
I don't know about that.
Well, I have to say, we've run out of time. It's been great. You guys have fun? Huh? Thank you so much, and may the dark matter be with you.
Thank you, John.
Thank you.
Thank you, John.
Thank you.